Hey, there we go. So welcome everybody today. I'm Paul Schultz. I'm the senior data scientist and statistician for the Population Dynamics and Health program. I want to talk a little bit about the center before we get started, just to we're a smaller center that's kind of new, and we're growing. These workshops are part of sort of our promotion and outreach, so I just want to take a couple minutes before we get started on the workshop and talk about who we are and what we're doing. You can see our website's up here. Hopefully you've landed here at some point, just at least to RSVP for the workshop. So we're sort of a sister center within the Population Studies Center here at ISR, with a charge of sort of supporting population research, and specifically that's will result in funding to the NICHD Population Dynamics branch. So we sort of have a growing list of faculty affiliates, and we're sort of charged with helping them kind of develop proposals and really manage whatever research needs they have that's in the field of population research. So I want to talk a little bit about the services we offer. We have obviously the workshop program that you're aware of now, that you're attending now. This is sort of a free outreach that we do. It doesn't require any affiliateship. It's free and open to the public. But we do have resources that are available to affiliates only. We offer free consulting, really in terms of anything related to population research, data management, modeling, statistics, really any and all things relevant to your research. We also offer a small grants program as well as a mentorship program as well. Most of the details are available on our website. You can feel free to read about it there. If you have questions, you can contact me directly. And if you or anyone on your team is a junior faculty specifically, or really faculty at all that's doing population research, feel free to investigate this affiliateship program. So today's workshop's going to be. Oh, sorry.
One thing about the grants.
Yes.
If you are not a faculty member, but you're interested in in trying to get some of the small grants, go to one of our faculty affiliates and see if they're interested in collaborating with you. We would love to have this spark new opportunities for collaboration. We're constrained by the NIH to have this money channeled towards our faculty affiliates. This is designed mainly for faculty development, but that doesn't mean that you can't collaborate with them. You're not faculty members.
That's exactly right. Basically, if you're affiliated with a faculty affiliate, so if you sort of have a second order affiliateship, the faculty member doesn't necessarily need to be in the room to get these resources. Really, if you have any research connection to an eligible faculty affiliate, you are then eligible to get all these resources that we're talking about. So, any questions with that? Okay, so I want to talk a little bit about the upcoming workshops. So we're trying to have these once a month. We've been having these monthly, I think, since May. So I see a couple of familiar faces here today. Our workshop in October is going to be about machine learning and social science. Feel free to RSVP for that. We'll have the information up on the website probably by the end of this week, and we'll have the RSVP system open. That's going to be on October 25th, I believe. And then we're still sorting out the time, but be on the lookout for that. And then a quick follow-up in November, then we'll be doing sort of a follow-up to this workshop with Rick Valiant of the JPSM, where we'll be talking about, this workshop today is going to sort of set you up on the importance of building the design structure into your analysis and also using the weights. And then the November workshop is going to actually talk a little bit more about weight creation itself and focus more about just the actual the weight dimension of your analysis. So I think that's it for that. As far as the workshop today, if you're on Blue Jeans, I know a lot of you are online. I'll be monitoring the chat, so feel free if you have questions. Those of you that are online, just go ahead and send those questions to the chat, and then I'll read them sort of to the people in the room. For those in the room, obviously, feel free to just raise your hand and ask questions at any time. I believe that's it. Oh, I have this orange folder here. I'll be passing this around. So I would like you to sign in. This helps us kind of justify to our funders just like the kind of numbers we're getting and sort of who we're reaching. So if you wouldn't mind just signing that, and we have a little field there. You can note kind of what center you're affiliated with. We're not going to track you or anything. It's just to really help us kind of understand who we're reaching with these, and kind of to be able to report back to our funder. And then also we're very interested in your feedback. Again, this is a new center. This is like our 6th workshop, so we're still growing everything, and we're still getting better at putting these on. So we absolutely value your feedback. We have the paper form here. If you wouldn't mind grabbing one, and then if you need to leave early, please just make sure that you fill that out before you leave. And then for those online or whoever doesn't fill out one of these paper ones today, I will be sending you also the same thing in a web format so you can answer online later. And obviously these are anonymous. It's really just to get your feedback so that we can improve. So I think that's it for me. Any questions at all before we begin? All right. So I'm going to introduce our speaker. He's also, what's your title? Do you want to say your title is in terms of the center?
Yeah. So there's three main cores in the center, and I'm the director of the scientific and technical core, the population dynamics and health program. So that's kind of where I'm coming from. So Paul just said everything that I usually try to say before the workshop. So thanks, Paul.
Yeah, no problem. So Brady T. West is a research associate professor in the survey methodology program located within the Survey Research Center at the Institute for Social Research on the University of Michigan Ann Arbor campus. He earned his PhD from the Michigan program in survey methodology in 2011. Before that, he received an MA in applied statistics from the U of M Statistics Department in 2002, being recognized as an outstanding first-year applied master's student, and a BS in statistics with highest honors and highest distinction from the U of M Statistics Department in 2001. His current research interests include the implication of measurement error and auxiliary variables and survey paradata for survey estimation, survey non-response, interviewer effects, and multi-level regression models for clustered and longitudinal data. He's the lead author of a book comparing different statistical software packages in terms of their mixed effects modeling procedures entitled Linear Mixed Models, a Practical Guide Using Statistical Software. And he is a co-author of a second book entitled Applied Survey Data Analysis with Stephen Haringa and Pat Berglund. Okay, that's it. Let's welcome our speaker, Brady West, and thanks to everybody for coming.
Thanks, Paul, for that really nice introduction, and thanks to everybody as well who's joining online. It was great to see that so many people were interested in this particular topic, so we've been really looking forward to the workshop today. We do have a big audience, but I want to encourage you to just stop and ask questions at any point. And if you're in Ann Arbor right now and you have a question, I'll just relay that for people who are online in case you can't hear. And people who are online, feel free to interrupt as well. If you have any questions, just make yourself known, and then we'll try to do our best to address your question. I also want to reiterate what Paul just said. So if you're online, feel free to type a question to the chat message box, and Paul will gather those, and then we'll have multiple opportunities for question and answer sessions throughout the course of the morning. Okay, so I'm just going to pull up the slides here. So the title of this workshop is Design-Based Analysis of Survey Data. So that's going to be our primary focus today is design-based analysis, but we'll also talk about model-based alternatives to analyzing survey data and talk about those distinctions. On this first slide, you can see my email address, bwest@umich.edu. Feel free to shoot me an email at any point during the workshop or after the workshop if you have questions that come to mind afterwards or you just didn't feel like sharing them during the workshop today. I'd be more than happy to correspond with you over email about any questions that you might have about the material that's going to be covered today. Okay, so here's an overview of what we'll be talking about this morning and then into this afternoon. I want to talk about what exactly we mean by complex sample survey data. So this is a term that gets tossed around a lot, and I want to formalize it a little bit more in thinking about how to approach these kinds of analyses. I want to define design-based analysis and, again, contrast that with a model-based analysis approach to survey data. We're going to spend some time talking about appropriate versus inappropriate analytic approaches. So when you're sitting down with a survey data set, what are some of the things that you need to think about, features of survey data that you need to look for when you're first getting used to a survey data set. I want to talk about a meta-analysis that I recently performed. This was funded by the National Science Foundation to see what users of survey data were exactly doing with data that the government produces. So I want to talk about a meta-analysis of analytic error, and I'll define what I mean by analytic error and talk about the implications of analytic error, but we'll talk about that issue among people who are doing secondary analyses of survey data. And then the second part of the workshop is really going to go into a variety of different examples using real survey data to perform analyses. And the primary focus is going to be on Stata and SAS. But if you have a question about doing this kind of stuff in any other software, I'd be more than happy to receive those questions. We focused on Stata and SAS just because of the audience that we thought we were going to get with this particular workshop. But again, if you have questions about anything else, feel free to email me. Feel free to message the chat room. Feel free to stop me during the discussion. More than happy to talk about different software options. And then at the end of the slides, everybody will be able to get these. You should have received them via email. You can also download them from the PDHP website. I've included references that I'll be referring to as we go through the day today, some of the key readings in this material that we'll be talking about. I also have up front here in Ann Arbor a couple of the key books, recent books in this area that have come out that I think are extraordinarily valuable if you're not a survey statistician, but you want to do these kinds of analyses. So feel free to come up at any point and just take a look at these books. I'll also be pointing out different features of them as we go through the workshop. Okay, so let's just start with a definition of what is complex sample survey data. I like to move around when I'm talking, but I have constraints here so that I can stay on the camera, so I'll kind of move around in this area over here. I might go over there sometimes, but that means I'm going to be off camera, so I'll just try to be loud throughout. Okay, but what is complex sample survey data? So many survey data sets, when you're downloading a data set from online or from a government archive or from an existing project, these data sets are often collected from units that are randomly selected according to a very fixed scientific sample design. And notice what I bold on this slide, stratified, multi-stage sample design. When you're reading about a survey data set, these are key words that you should look for in thinking about whether there are complex sampling features, okay? Stratification, multi-stage sampling, those are very important words that should set off a light bulb that says, I need to take a more specialized approach to this kind of analysis. Most of the survey data sets that you download from these kinds of archives for secondary analysis do not arise from simple random samples. And unfortunately, when you first learn about statistical analysis in your introductory stats course or regression courses or whatever the case may be, all of those methods are designed for simple random samples. Okay? So there's this kind of disconnect between the types of data sets that are often created by different research programs for public use and what's being taught in introductory statistical classes. Most of the time we focus on simple random samples in classes that are part of many degree programs. So when you see these words, those should immediately set off a red flag in your mind that says, I can't use standard analysis methods for these types of data sets. Okay, just want to make that very clear up front. So we'll keep coming back to that idea of stratified and multi-stage. Okay, so as I mentioned, introductory stat classes often assume that you're working with data from a simple random sample, where at the simplest case, the units in your data set were just randomly selected from some larger list of units. Again, that's the working assumption that we have. Some of you may have heard the term IID, or independent and identically distributed. That's typically the assumption that we're working with when we first learn about basic statistical procedures. And then those kind of go out the door when we're talking about these types of data sets. That's the key thing to keep in mind here. Okay? So simple random sampling is seldom what actually happens in real-world samples, especially samples that are selected from very widespread populations geographically. In many cases, it's just not feasible financially to select a simple random sample from a very large and widespread population. So the sample design itself has to introduce cost efficiency so that we can actually collect the data within some kind of fixed budget. So complex samples are anything that are not simple random samples in these cases. Okay? Anything that goes above and beyond simple random selection of elements from some population list. And generally, the three key design features that lead to this definition of calling something a complex sample include stratification, and we'll talk about what that means, cluster sampling, so this is part of the multi-stage definition of these kinds of samples, and then weighting of survey respondents. So Paul talked about how we're going to have this upcoming workshop that focuses specifically on survey weights. Today, we're going to talk about what to do with survey weights when it comes to analysis. In November, Rick Valiant's going to go into a little bit more detail where if you're working on a project that involves complex sampling and your team needs to design weights that reflect the sample design that was used, how exactly do you do that? So we're not going to dive too far into the creation of weights today. We're going to be talking about if you've been provided with weights in a data set, how do we go about using those for analysis? That's our focus today. Okay? But when we talk about whether or not we have a complex sample in hand, any of these three features count. So if your data set, if the sample design purely involves stratification and no other sampling like cluster sampling or anything else, that's a complex sample because it's deviating from a simple random sample. If your sample design involved cluster sampling, you selected clusters of units like hospitals or neighborhoods or census blocks or whatever the case may be, that's a complex sample, even if they weren't stratified in some way. We'll get back to these terms in more detail. And if you have weights in a survey data set, that generally means that the cases that were sampled had different probabilities of being included in that sample. And we need to account for those different probabilities when we sit down to analyze the data. So you don't have to have all three of these features for something to be a complex sample. You could have any one of the three or two of the three. And you're talking about something that is more complex than a simple random sample, where again, simple random sample is what we learned in intro stat classes. Okay, so today we're shifting our mindset from what we've learned already about in stats classes, and now we're turning about how to perform these kinds of analyses in a way that reflects the sample design. That's where this idea design base comes from. We're talking about how to do analyses that reflect the complex sample design that was actually used. So let's get into a little bit more about each of these different terms here. Stratification, this is where we divide the units in a given target population into groups or divisions or strata that are homogeneous within and heterogeneous between. That's a key feature of this kind of design here. We want those different strata to be as similar as possible in terms of what we're trying to measure to get the biggest increases in efficiency of our estimates, or basically to reduce the standard errors of our estimates as much as possible. The more different that those divisions of the populations are in terms of what we're trying to measure, the bigger the decreases in our standard errors. Okay? So this is why it's so especially important to account for stratification when you're working with these kinds of data sets that were collected from samples with complex designs, is because strata are specifically designed to reduce the standard errors of your estimates, give you more precise estimates. So if an analyst just looks in a data set and they say, oh, look, a stratum variable, and they say, I don't know what that means, so I'm going to ignore it. You're actually harming yourself. You're harming your analyses, because by design, that stratification was introduced to increase the efficiency of your estimates. So if you ignore that stratification, what generally is going to happen is that the standard errors that you compute and prepare for tables are going to be too big. And if standard errors are too big, confidence intervals are going to be too wide. And p-values are going to be too large. So stratification is a part of the design where if you design these fixed strata and you allocate your sample to each of these strata, you're removing that between stratum variance from the sampling variance calculation. It's a good thing. You're getting rid of the random variability in your sample estimates that comes from variability between strata, because you're allocating your sample to each of these different divisions by design. So you're always going to have sample coming from these different divisions. You're removing that element of sampling variability. So it's critical in the analysis to account for that so you can benefit from the gains in efficiency of your different estimates. Okay? Now, forming the strata, that generally requires having some kind of auxiliary information on the sampling frame that you're using. So you need some variables on your population list that you can use to divide that population into these different homogeneous groups. In the absence of those auxiliary variables, it's very difficult to try to formulate these kinds of strata. So you form these divisions, these groups, based on your knowledge of what variables are predictive of the variables that you ultimately want to measure. And then you allocate some fraction of the overall sample to each of the different strata. So this is what happens by design. As an analyst, you're not responsible for this. This is what goes on by design. You have Jeff?
Yeah, I was also wondering if another motivation for stratification is like to oversample certain groups.
Yep.
Is that up there? Okay.
Yeah, we're going to come back to that. Yep.
Sorry. Yeah.
Yep.
But
So
sometimes that may not go hand in hand with the goal of getting of the between and within.
Right. Right.
Okay.
Yep.
It's proportional.
Oh, question. What's that?
They're proportional, disproportional.
It could, yeah, there could be a variety of different ways that you allocate samples. So the question for those of you online was, how exactly is the sample allocated to these different groups? The people designing these samples, there are a variety of different choices that you could use for that. It could be proportionate. The amount of sample that you allocate to each of the different strata could be proportionate to the size of that stratum in the population. That introduces equal probabilities of selection for everybody and no need for weight. So, but that's just one option.
Yeah,
Like-
option. When we combine it, the proportion, each piece is selected. So doesn't that make it like simple random or no?
No, yeah,
No,
that's because simple random sample, you have to worry about between stratum variance. With stratified sampling, that's no longer part of the equation, right? That's a critical difference. Where they're the same is that with proportionate allocation, there's no need for weighting. That's the key similarity, but we still need to account for the gains in efficiency from doing that. So back to Jeff's point, we could come up with an allocation where we assign much more sample to a particular stratum than exists in the population proportionately, because we want more cases from that particular group. Maybe it's a minority race ethnicity group or something like that, where we want to have more representation from that group in our sample, given our objectives of our research. And that's what might introduce different probabilities of being selected, depending on what stratum you belong to. Yep. So that could be one goal as well.
That is accounted for.
Yes. Exactly. So that we're going to get back to weighting, but that different probability of selection, depending on what stratum you belong to, is what goes into the weight. The key, and we're going to keep talking about this, but the key mistake that a lot of people make is thinking that if I account for the weights in my analysis, I'm accounting for all these features of the complex design. And that's it, I'm done. What people often miss is that you also need to account for the stratification and the cluster sampling when you estimate your variances. Probably the most important theme today. We want to avoid that mistake of just thinking that if we plug the weights into our estimation, we're good. That's not the case. Because if you fail to account for stratification, again, you're not getting these gains in efficiency for your estimates. That's a very important point here. Okay? So, how we allocate the sample, generally not your job as a secondary analyst. That's the sampling statisticians who work on a project, they figure out the best way to do that, given the objectives of the project and the available budget and so forth. So then you select samples within each of these different strata of the population. These could be simple random samples. So you could have a sample design where you allocate sample to different strata, and then you select simple random samples within those strata, okay, according to a certain design or a certain target. You could select cluster samples within each of those strata, select larger units that contain several elements, and then sample from within those. One of the key reasons to use stratification is that you ensure that you have representation from all those different strata. This is another key difference from simple random sampling. Just for example, consider a simple random sample from the 50 United States. Okay? In those 50 states, if we were to draw a simple random sample, it's equally likely that the entire sample could come from Florida, as it is that the sample comes from all 50 states. Simple random samples, that's possible because every sample is equally likely that you could select. So stratification is a design tool to prevent those bad samples, ensure more balanced distribution across the different strata. Okay? So there's really no bad points about stratification. It's got many positive design features, but as a secondary analyst, we want to make sure to account for it when we estimate our variances. Okay? So we draw these samples from each stratum. Then in estimation, we combine the estimates from the different strata to form overall estimates. And as we just talked about, this is where you may need weights, depending on how much sample was allocated to each of those strata. If there was oversampling or whatever the case may be, weights may reflect different probabilities of selection. And overall, when we account for this stratification in our analysis, again, this reduces the sampling variance of estimates. We're going to see a number of examples later where a failure to account for stratification is going to paint a very different picture of what's happening in terms of the precision of our estimates. Okay, so very important to account for this element of complex sampling. Any questions about stratification? Just kind of broad overview here. I mean, we usually spend a couple lectures on stratification in the degree program. So we're just giving an overview of why it's important for analysis here. Any questions? Okay.
Is stratification typically just on one dimension, or could it be on like a intersection of two?
So the question was, are strata generally formed based on one variable, or could they be formed based on cross classes of multiple variables? More often, they're formed on cross classes of multiple variables. So you could have, depending on what you have on your sampling frame, you could have geographic areas, you could have sociodemographic groups, you could have economic divisions. Usually these things are crossed because the finer stratification that you have, the more homogeneity you'll have within the strata. And the more homogeneity that you have, the lower your standard errors are going to be. So by design, we try to form strata that are, where again, the measures that we want to collect are as similar as possible within. So usually cross classes are the norm rather than the exception. That question? Okay, so that's stratification. Second key feature of complex samples, cluster sampling. Okay? So one essential difference right up front, strata are fixed by design. Okay? You form 20, 30, 50, 80, however many strata you want to divide your population, and every hypothetical sample that you might select is going to be allocated in the same way to all 80 strata. Those are fixed by design and they cover the entire population. In cluster sampling, clusters are randomly sampled. This is the key distinction. Strata are fixed by design. We're going to be talking a lot about stata, so it's easy to make that mistake. Strata are fixed by design. Clusters are randomly sampled. So another common mistake among secondary analysts is to interchange these terms. These are my clusters, these are my strata. Oh, that's the same thing. They're not. They're absolutely not the same thing. Okay? Clusters are units of elements of interest, like clinics or schools or counties or businesses, and usually that's all that we have on a sampling frame. We have a list of clusters rather than a list of people or more generally units that we want to work with. And we randomly select these clusters, either from within strata or from the overall list of clusters in the population. Clusters are randomly selected, so they introduce sampling variability. The more variable those clusters are, in terms of what we're trying to measure, the higher your standard errors will be. It depends on how those clusters are defined. But again, we randomly select clusters, we fix design strata. That's a key difference between these design features. Now, so why do we select clusters in the first place? Primarily to save money. That's the key point here. We pursue cluster sampling to save costs compared to simple random sampling. Think back again to my example of taking a sample from the entire United States. Okay? Do we want to have an interviewer or a data collector drive around to each individual address, knock on the door, then drive to a different address in Mississippi, then drive to an address in North Carolina? No. It's extremely cost inefficient to do that. So instead, what we do with these large, widespread populations is we randomly select these clusters, and then we send somebody to those clusters to work a random sample cases. This is the idea of multi-stage sampling. There might be multiple stages of randomly selecting clusters to the point where we get to the elements that we really want to work with, who are then randomly sampled again. Yep.
So, an example of clinics within states.
Yep.
States are your strata.
Right.
And clinics are your clusters.
Exactly.
Couldn't it also be that within each strata, randomly sample clusters, if you happen to get clinics that are all in rural areas?
Yep.
Right? So
it's a great point. You could further stratify within states by urban-rural.
okay.
And that's the cross-class question, right? So you could form your strata based on cross-classes of these different design features, and then randomly select your clusters within those cross-classes. Because you're very right. If the stratification is not very fine, you could run the risk of those bad simple random samples again, where all your clinics are rural. Whereas if you stratified by urban and rural within a state, and then you sampled clinics within those strata, you're getting more representation. And you're removing that sampling variable. That's the key. So good. That's a very good example. Okay. So the units within a cluster are often homogeneous, much like strata. These randomly sampled clusters tend to be the people within them tend to be very similar in terms of what we're trying to collect. But again, they're randomly selected. They're not fixed by design, like strata, where every sample would be drawn from the same exact strata. Okay? Again, clusters are often sampled across multiple stages, so you could have counties, blocks within counties, households within blocks, etc., all to save on money. What's the most cost-efficient way to get to the people that we ultimately want to measure? It's all done to save money. The drawback statistically is, and this is where you guys come in as secondary analysts, the drawback statistically is that the higher that correlation within clusters of what we're trying to measure, the higher that within cluster homogeneity, some of you may have heard of ICC, intra-class correlation. The higher that ICC, the higher your standard errors get because of the cluster sampling. The higher the ICC, the more variable those clusters are. The more variable those clusters are, the higher your standard errors are going to be because you're randomly sampling clusters. And if those clusters are all over the map, in terms of what those measures look like, your standard errors could go up. There could be more sampling variability. As a secondary analyst, the key point is to account for that cluster sampling. Because whereas stratification decreases your standard errors, cluster sampling increases your standard errors. And empirically, you want to account for that tug of war. If cluster sampling wins, it wins. But you need to account for that in the analysis. If stratification wins, you get lower standard errors. You want to account for that in your analysis. Okay? Both of these features need to be accounted for one way or another when you're performing design-based analysis. This is kind of the overlooked aspect of complex samples, is the role of stratification and cluster sampling in affecting your standard errors. We don't want to just use weights. We need to account for these features as well. So cluster sampling increases the sampling variance of your estimates. Okay? This is just a picture that's taken from this Applied Survey Data Analysis book. Again, you can feel free to come up and take a look at it. We actually borrowed this from somebody at Westat. Okay? They used this to describe one of their multi-stage sample designs. But what you can see from this picture is a typical 4-stage design that's drawn in the United States. Again, we're never going to just take a simple random sample of households from across the 50 states. Okay? We might first, at stage 1, draw a sample of counties. Those are the purple boxes that you see in this picture. Those are also called primary stage units, or PSUs, in this kind of sample design. So you hear that PSU term a lot when talking about sampling variance. So those purple counties are about 3,100 counties in the continental U.S. Those might be primary stage units. Okay? Then you blow up one of those purple boxes that you select, and within that county, there are different area segments, or neighborhoods, or census blocks, or something like that. Like, again, to save money, you might randomly select those area segments at stage 2. If your project can afford it, you might just draw a simple random sample within a purple county. It depends on what your project can afford and who you're trying to get to. Okay? So we might draw a sample of those yellow area segments within a given county. And then within those area segments, if you blow that up even further, that's where you can identify housing units. So you might send a field researcher out to that sampled segment to list all the housing units. Or you might buy a list of all the addresses in that census block. There are commercial vendors that make those kinds of lists available. And then within that list, you draw a sample of households. That gets us to stage 4, okay? Where within a sampled household, you roster that household. You see who's living there. You might screen that household for eligibility, and then you might pick one or more of the eligible people living in that particular household. This is a very common area probability sample design for large national samples. And this kind of idea might even be used within smaller areas. Okay, there's a variety of studies done here at ISR that focus on, like, the city of Detroit, for example. You can still employ these multi-stage designs within those smaller geographic areas because you're still talking about a pretty widespread population. So this is what we mean by multi-stage cluster sampling. And if you read about this type of design, again, should set off a red flag that in terms of analysis, I need to account for the cluster sampling that was conducted. Okay, questions? Any chat questions? Okay, so that's an important picture to keep in mind. So we've talked about those 2 key design features so far: stratification, division of the population into these different groups, and then cluster sampling, the random selection of naturally occurring clusters of units within those strata potentially, or just from our population list. So then there's survey weighting. Okay, survey weighting is kind of the third main piece that describes a complex sample. So in these complex samples that are often selected across multiple stages, the probabilities of selection into the sample are generally not going to be the same for different units. Sampling statisticians try as hard as they can to maintain equal probabilities of selection as deep into a multi-stage design as possible. Okay? So if we don't have to worry about weights, that's a better situation. Okay? Weights are a tool to compensate for different probabilities of selection. Ideally, ideal world, everybody would have the same probability of selection, like proportionate allocation, and we don't need to worry about weights. Unfortunately, when we're trying these cost-efficient designs, or we might oversample particular groups, different cases have different probabilities of being included in the sample. Okay, so the way to think about this is that if the probability of selection for a given case by design is defined to be 1 out of 100, that means that unit represents themselves and 99 other units like them in the population. Okay? So I had a 1 in 100 chance of being selected, so I have to speak up for 99 other units that weren't selected. That's the basic idea here. And so my weight might be 1 out of 100, your weight might be 1 out of 1,000. Somebody else's weight or somebody else's probability of selection might be 1 out of 10,000. Okay? This is what introduces the need for differential weighting. So a survey weight begins as the inverse of that probability of selection. So every single unit in the population in a probability sample, you can write down their probability of selection. Okay, you hear these terms, probability sampling, non-probability sampling. In a probability sample, we can write down a non-zero probability of selection for every single unit in the population. Once we know what that probability of selection is, like 1 out of 100, we invert that probability of selection. And that's what's called a design weight. Some projects call it a base weight. Okay? So in this 1 out of 100 case, that design weight is 100. Simple as the inverse of that probability of selection. That's where a weight starts. So somebody who has a 1 in 10,000 chance of being included in a sample, their weight starts as 10,000. That's where these weights begin, is in terms of these probabilities of selection. So the idea is that cases in the population that have a lower probability of selection get more weight in the analysis. They have to represent more people. So if we oversample, those cases get less weight in the analysis because they had a higher probability of selection. Okay, we have to downweight them to get a good picture of what the population looks like. So that's the basic intuitive idea. But again, Rick's class in November is going to go into a lot more detail about how these weights are developed. Okay? So you start with that design weight that reflects your probability of selection. I often tell the story in one of our projects here at Michigan, the National Survey of Family Growth. We oversample particular subgroups. There are certain targets that we want to focus on. And one time there was a gentleman who basically had a 0 probability of selection, given the groups that we wanted to oversample. He was a poor, I say poor in that it was unfortunate at his household characteristics. He was an older, single, white father living in a household with 4 teenage girls. Okay? I mean, without even talking about sampling, sounds like a rough situation. Okay? But in terms of this sample design, where teenagers were oversampled, girls were oversampled, his probability of selection was close to 0, given the circumstances of that household. And by a random chance, because we're doing random selection of cases, he was selected. So by the time you accounted for his probability of selection, in addition to the fact that a bunch of people like him didn't respond to the survey, so we have to adjust weights for that, and then we calibrated that weight, his weight was above 3 million. So again, think about what we mean by weights. Nothing wrong with what was done scientifically. We followed the letter of the law with a probability sample. His weight was something like 1 divided by 3 million. Okay? That means what that poor dad of 4 teenage daughters says on that big survey is going to speak for him and 2.99 million other people. Okay? Pretty important. We don't tell him that when he's answering the survey. But what he says is going to be pretty influential. So we're going to talk about weight trimming. There's another issue related to that, is that how do we need that weight of 3 million, or can we cut that down back to size without losing too much bias in our estimates? We'll come back to that idea. But these weights are often adjusted to correct for differential non-response across subgroups, and they might also be calibrated to what you know about the population. So for example, You might adjust those design weights to account for differential probabilities of responding to the survey, because not everybody's going to respond to the survey. And then you see that your weighted distribution of gender is something like 47-53. And you know in your population that it's 50-50. So even after you've adjusted those weights for non-response, it still looks like your weighted distributions are a little bit off. That's where calibration comes into play. We can apply an additional adjustment to make sure that our weighted sample is perfectly in line with what we know for the population. That's kind of a third adjustment that's applied to these weights. Okay? Again, Rick's class is going to go into a lot more detail. I have this book up here. Rick and his students, in particular Jill Deaver, they have been working there to the bone the last couple of years. Rick just retired. So he's doing this as an emeritus professor in November. They've been working their hands to the bone to basically get all of his knowledge about weighting down on paper. And this new book, Survey Weights, a step-by-step guide to calculation by Rick and, again, Jill Deaver, is probably the best single handbook or reference that I've seen about how to develop survey weights. I'm not just selling this because of state of press or anything like that. It's just a really good book. If you ever need to work on weights for a given project, it's an incredibly valuable resource. And he's written a larger textbook about the entire science of weighting probability samples. So he'll be talking about that a lot in November. Yep.
Do we make, for the last point that you made, do we make calibration 50-50, in this case male-female, only if the variable is important to our research, or nonetheless, if it's not important, for example, but we know that in the population it's 50-50, we don't make it. So this is the point.
That's part of the weight construction issue. We want to calibrate based on variables that are correlated with our key measures. Really doesn't help to calibrate based on factors that have nothing to do with what we're collecting in the survey. So Rick's going to go into that in great detail, how important that decision is. That's right. So I just use male-female as an example, but in general, the calibration factors should be things that are correlated with our key variables. Yep. Okay, so weights correct for unequal probability of selection, differential non-response, calibration adjustments, all of that generally is rolled into a single weight. So the reason that we use weights in the analysis is that if those weights are correlated with the variables that we're trying to measure, we need to use them to reduce the sampling bias in our estimates. If we oversampled certain subgroups or certain types of subgroups didn't respond or whatever the case may be, if those weights that result from that process have a correlation with the variables that we're ultimately interested in, whether it's for a regression model or whether it's for a descriptive estimate, we need to use those weights in estimation to remove that sampling bias. And there's a drawback. When we use those weights, they act kind of like cluster sampling in that they increase the variance of our estimates. This is another kind of forgotten aspect of complex sampling, is that you hear about using weights in estimation to reduce bias. Very important. But there's an unfortunate byproduct of that. The more variable that those weights are, the higher your standard errors get. So all of a sudden, that tug of war, it's being shifted to cluster sampling and weighting. Core stratification only has one person on his team. Cluster sampling and weighting have two, and they're both pretty influential. Usually, the standard errors tend to increase when you account for cluster sampling. Yep.
Yeah. Person is saying, I'm not sure if volunteer sampling is related to non-response bias, but for instance, if I'm getting volunteers to participate in a survey with no specific sampling design, is it still possible to create weights?
Great question. Okay, so that question from online said, what if I have a volunteer sample, which unfortunately is becoming the norm because they're cheap? What if I have a volunteer sample? That's a non-probability sample. Okay? Our short course today is primarily focusing on probability samples that lead to this ability to compute weights. Rick is also going to spend a lot of time talking about that very question. How do we compute weights for volunteer samples or convenience samples in a way that we can still make inference about a larger population? That is a brand new science. And again, Rick and his colleagues are leading the way in this particular area. There are techniques that have been developed, but there's still an active focus of research. So if you have a volunteer sample, an opt-in online panel, something like that, how do we develop reasonable weights given that we don't have a probability design? and we don't have a design weight to begin with. We don't even know what that probability of selection is. How do we still develop a weight? It's a brand new science, and that's one of the features of that workshop in November. I'll touch on it a little bit, but generally it's a different approach that's needed because, again, we don't know those design weights that we're talking about here. The weights that we're talking about here are computed based on probability sample designs. A volunteer sample is not a probability sample, so that's important to recognize.
Just to add to that point, you could still apply things like the calibration technique if a non-probability sample the same way you would a probability sample.
Yeah, so that's another approach that Rick is going to talk about, is that you could, you get a volunteer sample that's 30% males, 70% females, you could develop a weight that realigns that 50-50. But you have to be very careful about that process. Okay, other chat question? Okay, so we'll come back to issues related to weighting, but what's in bold is critical here. Okay, we're not going into great detail about how the weights are constructed, but when you see a weight variable in a survey data set that you're working with, you should look at that weight variable, and the first thing to think is that weight variable correlated with my key variables? One thing that people do when they jump into these data sets is they just throw the weight into estimation procedures and keep their fingers crossed that everything works out. If the weight is not correlated with your key variables, it will not affect your estimates at all, and it's just going to inflate your standard errors. That's where, as an analyst, you have to do some critical thinking and say, are these weights actually even necessary for this particular estimate? As a general principle, yes, they're important for design-based analysis. But for a given estimate that you, the analyst, want to work with, the weights that the survey data producer computed may not be relevant at all. Okay? So the first thing is not to plug the weight into estimation. The first thing is to do some descriptive analysis and look at the correlations of those weights with your key variables. Okay, question?
The key variables you mean are key outcome variable or any of the variables?
Any variables you measure. Covariates, outcomes, anything that you're ultimately going to be trying to analyze. Basically, if you think of a correlation matrix, just make sure the weight's in that correlation matrix. And scrutinize that to see how many variables are actually correlated with the weight, whatever role they play in your analysis. Yep.
I guess there's like a trade-off, bias,
Right.
variance, so like the correlation coefficient to measure that trade-off, like maybe it's not worth it because it's going to increase my variance.
Yeah, we're gonna come back to that issue later, like what you do in analysis. How do you assess this trade-off to see whether it's even worthwhile to use weight? And that's where something called the mean squared error comes in. We're going to come back to that assessment later on. But yeah, what's important at this point is to recognize the trade-off. We're not there yet. Great questions. Okay, so I've kind of already done this slide, but definitely save the date if these questions are of interest, or you're managing a project that's going to be responsible for computing survey weights and providing those weights to the public. Okay, so again, Rick's going to be here on November 12th, 2019 from 9 to 1. That's largely going to be a follow-up to today's workshop that talks about the specific details of how to compute weights, how to reflect non-response, how to calibrate, things of that sort, and then more on using the weights in analysis. And I mentioned that Valiant Beaver book is really what I view to be an essential practical reference on computing weights and then using them in analysis. Okay, so I'll come back to that book at other points in the workshop today. Okay, so let's just review. This is your one semester, 45-minute summary of complex sample designs. Okay, so stratification ensures population representation and tends to decrease sampling variance. Okay, we want homogeneous strata that are heterogeneous between. Okay, cluster sampling saves us money, which is good, but we have that trade-off in that it tends to increase sampling variance due to the fact that the clusters vary. There's an ICC. Okay. Weighting accounts for unequal probabilities of selection due to oversampling or multi-stage designs, or whatever the case may be. Weighting adjusts for non-response. Weighting helps us calibrate for the population. And that primarily is designed to reduce the bias in our estimates that might be introduced by the sample design. But weighting can also increase sampling variance if those weights are highly variable, and especially if they're not correlated with what we're trying to measure. Okay, so there's that trade-off. So in sum, if you want to make sound inferences about the target population from which your complex sample was selected, you need to carefully account for all of these sample design features in the analysis. Okay? Weights, generally going to affect your point estimates, could affect your variance. Stratification and cluster sampling strictly affect your sampling variance. Okay? Whether or not you account for stratification and cluster sampling, your estimates will stay the same. Okay? Cluster sampling and stratification affect your standard errors. It's critical to account for those in your overall analysis process. Okay? So questions about these basic features of complex samples? Chat? Any chat? Okay. Okay, so now that we know a little bit about complex samples, what exactly do we mean by design-based analysis? So most statistical courses are going to introduce what's called model-based analysis. Everything you learned in Intro to Stat is model-based analysis. Okay? You took a regression class, model-based analysis. Okay? Even if you've taken 5 stat classes, and you talked about structural equation modeling, model-based analysis. Okay? Design-based analysis is typically not taught, unfortunately, in degree-granting programs, in quantitative fielding. Okay? It's just a current shortcoming of graduate curriculum. I'm going to talk more about that when we discuss analytic error. Okay? It's just important to pick up this kind of skill when you're dealing with these kinds of survey data sets. So in model-based analysis, you as an analyst specify an appropriate model for a variable of interest. Okay? Maybe that variable is normally distributed. Maybe it's a Bernoulli variable. Maybe it's a gamma variable. Maybe it's a Poisson variable. You do a 2-sample t-test, you're assuming 2 normally distributed variables in your 2 subgroups. Okay? It's a model-based analysis. Right? So all of your inference about whatever it is you want to estimate, your means, your regression coefficients, your odds ratios, etc., all of that inference in model-based analysis is governed by the model that you specify. There's a lot of weight on you as a data analyst to make sure that you got the model right. Because if you get the model wrong, everything could go haywire. Okay? That's the key point about model-based analysis. Now, design-based analysis, which is our focus today, doesn't refer to selecting a model for every variable of interest. Design-based analysis is non-parametric. That means there's no underlying parametric model for the variables of interest. Everything about design-based analysis refers to the expected sampling distribution, as it's called, for an estimate that would arise under the sample design that was used to collect the data. So what's a sampling distribution? If you were to draw thousands of samples under the exact same design, just keep drawing samples over, and over again, okay? And compute the estimate that you're interested in for every one of those samples, and then plot those estimates, the result would be the sampling distribution. That's the idea. So hypothetical, repeated, random sampling according to the same complex sample design, what would that sampling distribution of estimates look like if you drew thousands and thousands of samples following that exact same design? Same stratification, same cluster sampling, same weighting. Okay? You're going to get one weighted estimate in your analysis. That is your point estimate of the parameter of interest following a design-based analysis approach. Okay, your weighted estimate is going to be your point estimate. The standard error of that point estimate is an estimate of the standard deviation of that sampling distribution. Okay, so let me just repeat that. Okay? Hypothetical, what would happen? Thousands of samples, compute the same estimate. What distribution would emerge? The standard error that you report in a design-based analysis is an estimate of the standard deviation of that distribution of estimates. Now you say, I learned that in Intro to Stat too, so what's the big deal? Okay? The big deal is that the sample design is going to affect what that sampling distribution looks like. So remember those 3 key points that we were just talking about. Cluster sampling, it's going to spread out that sampling distribution. Higher standard deviation. Stratification, going to shrink that sampling distribution. The use of weights in analysis, going to spread out that sampling distribution. So when we estimate the standard deviation of that sampling distribution, okay, we want our standard error. We want to make sure that that estimate of a standard deviation reflects the design that was used. That's the approach here.
What's the purpose of this design-based analysis? It's used only as a tool to estimate which Which procedure should we use, parametric or non-parametric for our models? No?
Nope, the key, so that's the third bullet point.
Okay.
The key with design-based analysis, what we're trying to do is we want to estimate the parameters of interest with respect to our sample design, okay? We want to make inference about a finite population from which the sample was drawn. So somewhere out there, like this classroom right now, if we include the people who are online, that's a finite population. We could draw a sample from that finite population. We might stratify it by males and females. Okay? We might cluster it somehow and sample rows in the classroom. That's sampling from a finite population, and we want to make inference about the parameters of interest in that finite population in a way that respects the sample design that was used. So was there oversampling? Was there stratification? Was there cluster sampling? Our goal is to make inference about some parameter of interest in that finite population and compute an estimate of variability associated with that estimate that reflects the design features.
Can you give some practical examples?
Yep. So suppose that I stratify this classroom, finite population. If I had the resources, I could ask each of you a survey question and compute a census estimate for the entire population. Be done with it. No need for a sample. I don't have millions of dollars. So I draw a sample of you, okay? I oversample males because I know males are less likely to respond to the survey. Males have a higher probability of selection, okay? If I was to ignore those weights because males had a higher probability of selection, my sample would be biased to what males say on my survey question, okay? Knowing what happened in the design that I oversampled males in that finite population, I need to use that weight to compute my point estimate of that finite population parameter. Okay? But I'm not done. My standard error of that weighted estimate needs to reflect the fact that I stratified. I had some males, some females. Okay? And so now my standard error reflects the fact that I had oversampling and I used stratified sampling. So I have a point estimate of a finite population parameter with a good estimate of the variability that was introduced by the sample design. If I took a typical model-based approach and I just said that my variable followed a normal distribution and I calculated the simple mean, what would be the problem?
Don't get the estimates. We don't
get the right estimate.
Yeah.
It's a biased estimate. The design-based approach ensures that if I'm using the weights, that feature of the sample design is explicitly accounted for in the estimation process. So the modeler is going to say, as long as I get the model right, I'm going to get the right estimate. But if they completely ignore that feature of the sample design, their basic descriptive estimates are all going to be wrong. That's the difference.
It's like more for descriptive analysis, or
We're going to come back to that. So you're thinking about regression modeling. There's more of a debate about whether to use weights and so forth when fitting regression models. We're going to come back to that later in the short course. Yep. Thank you. Yep. Other questions so far? These are great questions. Other questions? Okay. So with design-based analysis, again, just to summarize, we estimate our parameters of interest based on the sample design, and then you estimate the variance of those parameters with respect to sample design. So what I was saying earlier is that if you just use the weights in estimation, you're going to get a great point estimate. That's fine. But the weights by themselves are not going to give you the correct standard error. That's such a common mistake that people make. The correct standard error is going to come from accounting for the stratification and the cluster sampling that's often employed. Yep, Jeff.
Yeah, there are two questions.
Yes.
One of them is asking for example. So as a code, I'm trying to sample migrants, mobile workers and seasonal farm workers in the state of Michigan.
Okay.
So how can I capture the seasonal fluctuation in the agriculture workforce? How can I capture the regional and seasonal stuff in the level of farm employment? Can you provide an example for this?
So we have to be careful about this course because it's all about analysis. So what I'm introducing in terms of the sample design stuff right now is what we need to account for in secondary analysis. That's a very good question, but it's a question about sample design. So I want to kind of avoid those questions for right now. There are certainly techniques where you can oversample hard to reach populations, but that's just not our focus today. Okay, so our focus is going to be on analysis. What we're introducing about sample design right now is just to motivate what we need to account for in secondary analysis. So whoever asked that question, I'd be happy to entertain that via email, But just to be clear, we're not primarily focused on sample design.
The other question is like, is there a limit to how many factors you can consider to create a weight? For instance, you are talking about like using a person's sex to create weights.
Yep.
Like, could we consider like gender, age,
Yep.
education level, and a lot of more?
Yep, you can consider a number of different factors when you can create a weight. And usually what Chen, that question's referring to is the weight adjustments.
Yeah.
So you could adjust for multiple different subgroup memberships in non-response adjustment, in calibration adjustment. It really depends on the factors that are most relevant for what you're trying to measure. That's the key. So it's the same question that came up earlier. If gender doesn't matter for my variables of interest, it's not correlated, it may not make any sense to calibrate my weights based on gender. But if there are several other factors that may matter, certainly you can account for those. So it depends on the most important factors related to the variables you're trying to measure. Okay, other questions? This is great. Great questions. Okay, so questions about what we mean by design-based analysis. Any questions about this definition here, what we mean? So everything is done with respect to the sample design, no assumed models for the variables of interest. All based on the sampling distribution according to a given complex sample design. Okay, so question, how do we estimate that standard deviation? We're only drawing one sample, right? We're not drawing thousands of samples. So how do we estimate that one standard deviation based on one sample? That's the art and the science of survey statistics. That's what we're going to be talking about today. How to estimate that standard deviation based on just one sample. Okay, so that's what's critical here. Yep.
Here in the design-based analysis refers to expected sampling distribution. So do we always expect the sampling distribution to be normal, or we work with also populations which are not normal?
Based on the central limit theorem, design-based analysis generally assumes that with a large enough sample, that does approach normality, right? So, but certainly there are some estimates, point estimates, that may not follow a normal sampling distribution. There are more advanced techniques for dealing with that. But for general estimates and design, yeah, that's the key of what that drives things here, right? Okay. Any other questions about design-based? Okay. Okay, so design-based analysis focuses our inference on a well-defined and finite target population. So this is what's absolutely critical relative to model-based analysis. In model-based analysis, once you assume that a variable follows a particular distribution, it's like you have an infinite data-generating machine. That distribution just defines a machine. It's infinitely spitting out data. With design-based analysis, there's one finite target population that we're interested in, and we want to calculate good estimates for that finite population from which our sample is selected. It's a big difference from model-based analysis. There's a focus on one finite target population where if we had the resources, we could measure everyone in that finite target population. We're not estimating the parameters of an infinite data-generating machine. Okay, so with model-based analysis, all of that inference is based on the specified probability model. There's no notion of a finite population with model-based approaches. Okay? So if you do a good job specifying that model and you're accounting for oversampling, you're accounting for other features of the design in that model, and you're not as worried about finite population inference, model-based analysis can be much more efficient, lower standard errors, and it can be very powerful. So I'm not up here to knock model-based analysis. It does a great job in many cases if you do a good job of specifying the model and accounting for design features in that model. But like I just said in that example with oversampling, that's a place where model-based analysis can fail if the analyst doesn't account for that oversampling in their model. Okay? So that's where design-based analysis is attractive, to account for these kinds of design features. Okay? So I reference, and this is going to be in the references at the end here, a 1983 paper by Hansen and colleagues. I still haven't seen a better comparison of model-based versus design-based analysis. Okay? It's 36 years old, but it's still 100% worth reading. Okay? It lays out this comparison in great detail. It's an easy read. It's not a statistical article, even though it's in JASTA. Okay? It's an easy read that talks about comparing these two inferential techniques and the advantages of design-based analysis for focusing on finite populations. I would highly, Highly recommend it, especially if you're in debates with your colleagues about which kind of approach to take. Okay? It's a great article to read, great article to cite when talking about these kinds of approaches. Okay, so we've talked about design-based versus model-based. What would be considered appropriate design-based approaches, given everything that we've discussed so far? Okay, so point number one, use those final survey weights for estimation, especially if they shift the estimates of interest substantially relative to ignoring the weights, okay, without changing the standard error substantially. Okay, and this gets back to what I was saying earlier. Look at the correlations of your weights with your variables of interest, because the weights may not be necessary. So in other words, a blind approach of just using the weights in every single analysis may give you standard errors that are unnecessarily large. Okay? The weights are critically important, but they may not be important for every single estimate that you want to work with. That's the key message here. Okay, so critical thinking about whether the weights are correlated with the variables that you're looking at. That's an easy descriptive analysis to perform. Okay. Number two, account for the effects on the sampling variance of weighting, stratification, and cluster sampling via these specialized variance estimation techniques. These techniques have been designed, researched extensively over the years, since about the mid-1900s, as a way of estimating that standard deviation of the sampling distribution. That's the whole focus here. Different techniques have been developed. Some are better in some situations than others. But in general, for complex samples, these variance estimation techniques include Taylor series linearization. That's the default in most statistical software, including SAS and Stata, that we'll be talking about. And linearization is just a way to take into account the weights, the stratification, and the cluster sample when computing variances of estimates. Okay? As an alternative, you can also use what are called replication techniques to estimate variances. This is like jackknife replication, balance repeated replication, bootstrapping is another technique that can be used here. The point is that whether you're using one of these two techniques or the other, okay, use those techniques to estimate the variances because they're specifically designed to estimate that standard deviation in a way that accounts for the sample design that was used. That's what's critical. For most common estimates, these two techniques are not going to give you different standard errors. The key is that you use one of them. And we'll talk about reasons to use one or the other as we keep going. Okay, so we have our point estimate, we have our standard error. Then number three, we could generate confidence intervals for the parameters that we're interested in. But there's one more piece that we need. So you all can think about the basic way to form a confidence interval. Point estimate plus or minus a critical t-value times the standard error. Okay? One more piece that we need is the appropriate degrees of freedom for that critical t-value. Okay? And in complex samples, it's no longer n minus 1. It's no longer the sample size minus 1 because we're estimating the standard errors based on the cluster. Not based on the individual elements, but based on the cluster. So now these degrees of freedom become, as a general rule, the number of clusters that you have in your data set minus the number of straight errors. So you might have a data set with 30,000 respondents, and you say, wow, my degrees of freedom are 30,000. But if that data set came from a sample design that only selected 30 clusters from 15 strata, you have 15 degrees of freedom for that critical t-value. Again, to reflect the sample design that was used to estimate the variance.
There is a question talking about like given what you are saying about like design-based analysis, does this change our interpretation about the 95% confidence intervals?
No. Yeah. So when you form a confidence interval, this doesn't change anything about how you interpret that confidence interval. And I should give you guys a pop quiz to ask how to interpret a confidence interval. Okay. I won't. But it doesn't change the definition of a confidence interval. Okay. Where again, if you compute that interval multiple times, what percentage of those intervals would cover the true population parameter? Not saying that 95% of values lie within that interval following this design-based approach. That is incorrect. It's saying if you computed this interval hundreds or even thousands of times, what percentage of those intervals would cover your true population parameter? So if I say 95%, that says 95% of intervals computed this way would cover my true finite population parameter. When we use design-based analysis procedures, we want to make sure that those confidence intervals are doing a good job of covering that true population parameter at the stated rate. So if you fail to account for stratification or clustering, your coverage might not actually be 95%. It might be 90, it might be 80. And so your intervals are not having the stated coverage. Okay? So back to Chen's question in the chat, this approach doesn't change how you interpret the confidence intervals. A design-based approach changes what you input to the confidence intervals. You now have a weighted point estimate, you now have a design-based standard error, you now have a critical t-value that reflects the degrees of freedom. The inputs are different. The interpretation doesn't change.
Point number one,
Yep.
are you going to talk later about what to do if your weighted estimates differ a lot from your unweighted estimates, and what are some good techniques to diagnose what could be possible?
Yep, we're going to talk about that exact question. Okay, so this is kind of a recipe for what I would call an appropriate design-based analysis approach. And what we want to prevent users from doing with this workshop is stopping at 1. Okay? Some people don't even get to 1. They start at 0, and they use approaches for simple random samples. But don't stop at 1. The standard errors need to fully reflect the design that was used. And that's what we're going to talk about how to do. Okay, so inappropriate approaches. Okay? A bunch of do nots. Do not ignore the weights entirely. Okay? Some fields debate about this. Like if you talk to an economist, they'll say, I hate weights, which is fine. If you think you have a good model, fire away. Okay? But for people analyzing survey data who, again, want to make these inferences about finite populations, they can be critically important, especially for descriptive estimates. We'll come back to regression later. But don't ignore the weights entirely, especially if they're correlated with variables of interest, okay? And you desire finite population methods. Okay? If you're a modeler, at least consider them as a covariate, for example. That might capture information about the sample design. Don't just throw them out. There are people who work here at ISR who spend half their time during the week maintaining weights for different projects. They're critically important for finite population inference. And when analysts just say, I don't know what this means, so I'm going to ignore it, everything we just talked about goes out the window. It's just a tremendous waste of resources. And it's going to give you incorrect estimates to boot. Number 2, do not ignore the stratification and cluster sampling when estimating sampling variance. Okay? This kind of information is generally provided in public use survey data sets either via specific variables that contain the stratum and cluster codes or via what are called replicate weights. We'll come back to replicate weights later. But in short, you might see a survey data set that has 100 different weight variables tacked onto the end of it. Okay? Those weights have been specifically designed for replicate variance estimation, where you can repeatedly compute your weighted estimates and then look at the variability of those weighted estimates across those replicate weights. That's strictly designed for variance estimation purposes in a way that captures the stratification and cluster sampling. So again, it's not just being afraid of seeing 100 or 1,000 or 500, whatever it is, different weights at the end of a data set. It's being aware that those are probably provided for variance estimation purposes. We'll come back to that. Number 3, do not consider model-based approaches that completely ignore these sample design features. Okay? I mentioned this a little bit already, but maybe the weight should be included as a covariate. Because observations within a randomly sampled cluster tend to be correlated with each other, maybe your model needs to include random cluster effects to account for that correlation. That's a dependency in the data that was introduced by the design used to collect the data. So a model-based approach needs to reflect that dependency. Okay? Otherwise, you're getting incorrect estimates of sample variance. Okay? Number 4. Oh, yeah, question.
I noticed when people do microcomputation for survey data, they usually assume their complex sample design is ignorable. So if that's not a proper way, so how to address that?
Great question. So for people online, the question was, suppose you're doing multiple computation as a tool for trying to predict what the missing values were in a data set. Should the design features that we've been talking about, weights, strata, cluster variables, be accounted for in that process? The answer is yes. Okay, just assuming that it's ignorable could lead to incorrect predictions of those missing values. And it's funny that you bring that question up because there's a brand new article. It just came out like literally last week about a new state-of-the-art technique for accounting for weights in those multiple imputation procedures. Like literally just came out last week. So that's an active area of research. But the short answer is you never want to just blindly assume that the sample design features are ignorable. So your imputation models should account for the design features in some way, in the same spirit as doing using a model-based approach that accounts for these features. But I'm more than happy to share that article if you shoot me an email. Like it literally just came out. Yep.
So, for example, design variables in the covariates when you do the micro.
That's one approach. Okay. There are more sophisticated approaches, but that's one potential approach, right? So your imputation models might include random cluster effects. That's one approach. But that's what I'm saying. This new article presents a brand new approach that I hadn't honestly thought of before. It's very clever. And they show via simulation that works pretty well for imputation. Yep. And it can lead to incorrect estimates if you fail to account for the sample design in the imputation process. That's another finding that they have. Question? Yep.
You might get into this when you do the examples,
yeah.
But we all love to use different names for things.
Yeah.
So variance or the primary sampling unit in Stata, that's the cluster, right?
Yeah. So that's a great question. So different data producers will give different names to cluster variables. Like one data producer might call it like var PSU. Another data producer might call it SIKU. Like it's just all over the map. So the key thing to do is read the documentation for that survey data set and track down these keywords like multi-stage, sampling error estimation, point estimation. And hopefully, if the documentation is well written, you'll get some guidance that says what variables to look for to account for these design features. We're actually writing an article about that right now. It's kind of a set of rubrics for how to evaluate data documentation. And we look at some different examples that may or may not give some favor to Michigan surveys. But thanks, David. We're giving many props to ICPSR. So. Okay, other questions about the kind of do-nots here? Okay. So let's see. This might be a good time for a break, actually. So where are we at? It's about 10:25. Why don't we take about a 10-minute break? Because now I want to get into, so we've talked about these concepts. What can go wrong? So suppose that you're doing a secondary analysis and you are, naively ignore these features. What can happen? So I want to talk about a little meta-analysis that we did about how often that happens. And if it does happen, what could the implications be? Okay, so we'll talk about that after.
The last question. So can you please provide reference to the articles discussing how to incorporating sample designs into the state of Michigan?
Into the what?
The state of Michigan.
Into this, I'm sorry, I didn't catch
the Michigan state, so like the whole Michigan. So they're asking how could you incorporating the sample design in the Michigan state?
In the Michigan state, like for what? I'm sorry, I'm not understanding.
So they don't mention any details in that.
I mean, there could be a variety of sample designs used in Michigan. Like you could sample counties, you could sample regions. I don't know. I'm not sure what question they're asking. So maybe just if whoever's asking that question, maybe if you could just expand on the question, I'd be more than happy to answer that. So. Like, or maybe a good example, like, so Jeff, like in DMAX, like what design do you guys use in Detroit, for example, roughly speaking?
What was the question?
Just like they're asking for an example of what design features might look like in a Michigan-based sample.
Yeah.
So like, just roughly speaking, what does DMAX look like?
Yeah, so we have this study, Detroit Metro Area Communities Study, and we do a multi-stage selection where we first sample, actually, in the latest iteration of this, we do some stratification. Then within each strata, we randomly select block groups, and then within those block groups, we select households.
Right. So it's not.
It makes the canvassing more cost effective.
So not a 4-stage design, but they divide block groups up into these different regions, and then they sample block groups, and then they sample households within those block groups.
Right.
Right. So more of a 2-stage design within Strata. But that's one hypothetical example, Chen. Maybe that's, I'm not sure if that's what you're
Yeah, and also like the section is on a specific reference to the new article.
Yeah, so what I can do is I can actually post that new article if people are interested in the imputation question. We'll post that new article on the PDHP website, so people can freely download it.
You know what journal it's in, or the author?
Journal of Survey Statistics and Methodology. I don't remember the authors off the top of my head, which was part of the reason I was surprised by the article. Like, it was a really clever approach, and yeah. Okay, other questions before we take a break here? Okay, yeah, let's break till about 10:35. So I'll start back up at 10:35 with this kind of study of analytic error, and we'll go from there. Okay.